Born-Haber cycles, and also on representing these cycles in what we'd call an energy level diagram. Okay. Now, when we've been calculating lattice energies in the last couple of lessons, you've effectively been using these Born-Haber cycles, okay? So the only difference here is now where we're going to try and show what's going on in the Born-Haber cycles with some sort of energy level diagram. It's actually not going to speed up your calculations at all. In fact, it's going to slow things down, but you might get asked to draw one of these. So that's why it's important that we go through it. You need to be able to draw an energy level diagram to represent these energy cycles. So that's why we must cover it. So let's put it into context by making it into a question. Up here, we've got a bunch of enthalpy values. And you can see this is all relating to lattice energy for the formation of sodium chloride, okay? So we've got the delta H formation at NaCl, delta H atomization, first ionization energy of sodium, delta H atomization of chlorine, and first electron affinity of chlorine. All these values, as you already know, will allow you to calculate lattice energy. So the question could be asking you to calculate lattice energy and show an energy level diagram in order to do that. So really, you can actually do this calculation already. I know you won't find it too difficult, but let's draw the energy level diagram as well. So when you do these energy level diagrams, the first thing you're going to do is to write down the elements in their standard state somewhere on the left-hand side of your page. So I'll do that quickly. So there we have it. Sodium exists as a solid, chlorine exists as a gas. So we've written them down now in their standard states, and then we're going to just have to show the changes that they're going to need to go through in order to eventually form a lattice, basically. If we talk about the end point here, well, what is the end point? The end point is actually forming sodium chloride. So I would probably put down NaCl down here, because we know that we're going to kind of cycle round to eventually end up here. You don't have to do this though. Right, the other thing that I should have changed here, we know that in order to form NaCl, then we're going to have to halve the amount of chlorine in here in order to make sure that is balanced. Okay, so I put the half in there. Right, so we're just going to go through step by step. I've done this a little bit big, so I'm probably going to make it a little bit smaller. So we've got space. So that's our starting point. So what do we actually have to do here? Well, the sodium has to become atomized. It has to become gaseous atoms. So we show that as the step that's going on here. So we convert that sodium into gas. Now, we could do multiple things at the same time here, and it would speed things up, but you're not supposed to, unfortunately. So we just continue. So you can see we've kind of covered, oops, yeah, that's okay. We've covered the change of atomization there for the sodium. So which value were we talking about here? Well, it's going to be this value here. And we could put that value in there. We know that that value is going to be plus 107. Now let's continue focusing on the sodium. The next thing that would require happening would be that you'd need to ionize that sodium. In other words, that needs to lose an electron to become a mole of scattered gaseous atoms. Obviously, there's no change here to the chlorine at the moment, okay, because we're doing one thing at a time. Excuse the terrible writing. So that now covers this here, the first ionization energy there. So the value in here would be plus 496. Notice as arrows are going up, they're all going to be plus values. That's very important to recognize. The next thing I'm going to show now, we've dealt with the sodium, so I just write that in as it was previously. Now we've got to make sure we've dealt with atomizing the chlorine. So we're doing this right here. Okay, and effectively what that means is we just want one chlorine gas, 1 mole, let's say, being produced there. And the value going in is plus 122. 1, 2, 2. It's all getting a bit messy there. So let's just make sure I've got my enthalpy values circled in red so we know what's going on. Now those are all endothermic processes from our starting point. Now it's very important you understand why I am now pointing this arrow downwards, because if I look at my value that I've been given, we can see that in order to turn this chlorine atom into a scattered gaseous ion, we're talking about an exothermic process here, because the first ionization energy of chlorine is exothermic, it's a minus value. So this is why I'm now going downwards on my energy level diagram. So I'll just write out what's actually happened there. And it's probably also worth putting in a line at the top. That's kind of showing, we've shown now all our exothermic, sorry, all our endothermic processes happening, and we've got to that point. Now we're onto the exothermic process here. And from that, we're going to have, or we're going to arrive at this point where we've got scattered gaseous sodium and we've got scattered gaseous ions of chlorine. And the energy change that's happened there is this value here. So we've now used 4 of our 5 provided values. That is minus 349. Let's make sure that's circled in red. That's supposed to be a 9 there. And now we've basically completed the cycle. I'll move this across. Let's continue that arrow down, because now we've actually got this equation. If we were writing out the lattice energy equation, this is exactly what it would be. It would be Na plus plus Cl minus, both in their gaseous states, to form 1 mole of NaCl. Okay, and I'll put a line, I'll draw a line down the bottom there. So we've now pretty much fully completed our energy cycle. Now this value here, if I put in an arrow here, this would represent the enthalpy change of formation, okay? Because we're going from the standard states there, we've got sodium and chlorine in their standard states to form 1 mole of the compound. So this right here would be our enthalpy change of formation. So let's write that in. And there we have it. That's our Born-Haber cycle. And that would actually also allow us to calculate the lattice energy. So let's quickly do that. Now, in terms of understanding this is what's really, really key now that you get this. This value here, we are trying to calculate, but the problem is we can't do it. Experimentally, it's not possible to do it. So this is where Hess's law comes in. Effectively, we are going to calculate this value by taking the other roots, okay? So what is the other root? Well, it's this root. It's effectively going from this, we can call this our starting point. And then, of course, this bottom line here is our ending point. And remember, I put NaCl there. I should probably put it there as well. Okay, so effectively, this is our roots now. According to Hess's law, we can take this root. Oh, that's a terrible arrow. Let me undo that. Let's try again. I'm going to take this root from start here. Let's say we're going round like this and down like this to the end point here. Again, why do we have to go that way? Well, because all these values are measurable, but this value is not. This value here, we can't do, okay? But all these values are measurable, so let's just take the other root, according to Hess's law. So what's the thing to be careful with when you're actually doing the calculation? Similar to as we've been doing before, if you are doing the reverse process, you must reverse the sign. So if you're going against the direction of an arrow, you must reverse the sign. So here, as we're going this way, this sign, we're going against this arrow, therefore this sign must be reversed. We're going against this arrow, this sign must be reversed. We're going against this arrow, this sign must be reversed. We're going against this arrow, therefore it must be reversed. We're going with this arrow, which is this value here, remember. I can put that in there, minus 411. And we're going with that arrow, and that's why the sign will not be reversed there. So I've been teaching you how to do the previous calculations using this exact same technique, okay? As you can see, everything that would be on the left-hand side of the lattice energy equation, effectively we're reversing that sign. Anything that was on the right-hand side, we're keeping the same. So let's just do the calculation now. So we're just going to sum everything up. So that should be plus 349. This should be minus 122. This should be minus 496. This should be minus 107. And this one we're going with the arrows, so that's going to stay as a minus, minus 411. So there you have it. You add up all those values. You're going to come up with a value of minus 787. Ask yourself, does that make sense? Well, it should do because it's an exothermic process. So you've got that calculation correct, and that's how you do it. Now, this is nice, this cycle, because you start to really realize why the signs are the way they are. Unfortunately, in your textbook, it doesn't at any point really make it clear that the reason why the signs are the way they are is because you're taking this alternate route. Okay, so hopefully this makes more sense now. Right, I'm going to set you up with some examples. You're going to do exactly the same thing as I've been doing and calculate your lattice energy just like I have. So I think the best thing to do is to check out your textbooks on page 262, page 262. Question 7A and 7B. I'd like you to get those done. Question 7A is draw a Born-Haber cycle for aluminium oxide. And part B is to calculate the lattice energy of aluminium oxide using the data under the arrows in the sequence above. What I want to see you do is to convert that into an energy level diagram, okay? So you want an energy level diagram and calculate the lattice energy just like I did with the, what was it, sodium chloride example, okay? So please get that done and have a great day. Bye-bye.